So you're told that there's some kind of a field where there are treasures at various points, right? And then there's this wall that's given to you, and you have to pick one of the treasure points in such a way that the triangle it contains, that the triangle it forms with the wall has the most value of the treasure that's there, right? This is what you're told. This looks like a pretty weird problem. One simple way to do this is to take each of the triangles that are formed, right? So this point will form a triangle with the wall. That point forms a triangle. This point forms a triangle. This one forms a triangle, and this one forms a triangle. For each of the triangles, we can compute its value, and then you just report the one that's highest. Okay? It's not the area, because the area doesn't matter. You have to figure out which treasures are in that triangle, and you have to add up its value. Right? That's the simple version of this solution. The problem is, what's the problem? The problem is there are too many treasure points. So you're told that there are 10 to the 5, so that's what, 100,000 treasure points. And well, this is not a huge problem. Hi, Yash. X, it says, is up to 10 to the 9. That's just the coordinates. That has some impact on it, but it's not a huge problem. But this has a huge problem, because if you try doing each of the triangles, right? For every triangle, I have to check each of the other points and see if it's inside the triangle, and then I have to add the value of that treasure. So essentially, for n different triangles, I have to look at n different points, so that's an n squared solution, right? And n squared on 10 to the 5th is 10 to the 10, and you're getting in territory where you're unlikely to finish in a matter of seconds. So n squared solution is not going to work. That's what the whole challenge is about. And this is why so few people actually solve the problem, right? So the question is, how do we go about solving the problem without getting an n squared solution? Which means if you're not allowed n squared, then n log n is probably the solution you're looking for. This is roughly what you should have in your head. Okay? It could also be n squared divided by log n or something like this, but it can't be n squared. Somehow you've got to cut that down. So how do you do this? And this is where you have to use this thing called range trees. And let me explain what range trees are about. I forgot to bring my pens, sorry.
I'm not going to be here for today's session because I'm going to go to the clinic, and I have this pain in my abdomen. I'm just going to have it checked out.
Yeah, you better get it checked out. Make sure it's not your appendix.
Yeah, that's what I'm afraid of.
Yeah. Let us know.
Yeah.
Email me, yeah. All right, so what is the range search problem? The range search problem is the following. The classic range search problem is the following. So there's a one-dimensional version. Here's a one-dimensional range search problem. You're given a set of values. I'm going to show that on a real line like this. Okay, you're given a bunch of values, and your query is going to give you a range, and it's going to say between here and here. And your job is to report either the values that are in this range or the number of values that are in this range, something along those lines. So each of these things are going to be queries. Okay. And your input, you can pre-process it. You can do whatever you want with it. You can build fancy data structures with it. But you want to report your query solutions have to be returned very, very efficiently. Okay? If your query is small, then no, let's not go there. So if I can figure out between which two, so for instance, in the one-dimensional version, here is a simple thing I can do. I could sort them. I could put it in an array. And if you ask me a query, the query will go from A to B. I can do a binary search for A, and it'll tell me where that falls. I can do a binary search for B. I'll know where it falls. And I know the index of those values. And I can immediately tell you how many values are there. And if necessary, I can report them. Right? So that's the simple solution for range search in one dimension. The problem is that there is also something called one-dimensional version, but the dynamic version. Now, what is a dynamic version? There may be values that get added in and inserted or deleted. And I have to still maintain the data structure and answer these queries as efficiently as possible. So if the data is dynamic, if I'm going to allow inserts and deletes, I can't store it in an array anymore. Right? So I have to store it in a fancier data structure. And what is that data structure? What is that data structure? Something simpler than that?
Binary search tree?
Just a regular binary search tree, a balanced binary search tree would work. Okay, even a red-black tree would work. But you have to augment that red-black tree with some additional information. And we can talk about that some other time. So if you do that, then it doesn't matter whether things are inserted or deleted, but I can dynamically answer any query you want in log n time. Okay, so essentially both these queries I want to be able to solve in order log n time. The pre-processing I can take as much as I want, as much time as I want, and typically we would allow for n log n pre-processing time. But that's done only once if necessary. In the dynamic case, I don't even do any pre-processing. I just have to say how updates are handled. And once I do that, I can answer these queries efficiently. So I know how to handle the one-dimensional case, because either I can store it in a sorted array or I can store it in a red-black tree, which is a balanced binary search tree. And once I do that, I can, with some extra work, I can solve this problem in log n time. The interesting case is when I go to two-dimensional or k-dimensional data sets. So in the two-dimensional case, I have the plane, and my points are points in the two-dimensional plane, and I may be inserting and deleting. And what does my query look like? What's a query here that's equivalent to the one-dimensional version?
A rectangle.
It's a rectangle, that's right. So I may have a rectangle that looks like this, and your job is to tell me how many points or which points are in this rectangle. Okay, so essentially you're taking a range on x and a range on y, and you're asking the query. So here it was all x. They were all on the x-axis, and so it was enough to just give you the x-coordinate A and the x-coordinate B. Here I have both x-coordinate and y-coordinate, so I'm going to have ax and bx, and then ay and by. So I'll give you the range in x and the range in y, and your job is to tell me how many points or which points are in this box. And you can easily generalize this to higher dimensions. Right? Now, what was I going to say? So again, the question is, how do I generalize the techniques I have here in order to solve this? I won't get into that right now. We can do this some other time. But essentially, it is a, for that, we have to first understand this solution properly before we go and talk about two-dimensional case. So that'll take some time. It's best we wait for a later lecture on this. But the general idea, if you want to know, is the following. In the one-dimensional case, we are doing a binary search tree. And I'm going to just draw it like this. It's just a binary search tree, just like you do. And essentially, you add some extra information. And then if I want all the values between A and B, sorry, A and B should be in red here. If I want all these values, then what I do is I search for A, and then I search for B, and then wherever it diverges, essentially I can process whatever is inside here in order to find the solution. So it's a bit complicated. We'll talk about this some other time. And so it's just a matter of traversing the subtree between A and B, which lies somewhere in here. Okay, and in fact, you can see that it'll look something like this. And so on. Okay. So by looking at all those subtrees, you can figure out all the things that are between A and B. And again, I'm just giving you a very quick sketch. We can go over this in greater detail some other time. Now, this is the one-dimensional version. Okay. What do we do for two-dimensional? So in two-dimensional, every point, here we assume that every point only has an x coordinate, right? So we're only looking at the x value, and we are processing it and looking at this range. Now we have both the x coordinate and the y coordinate. And this tree here knows nothing about its y coordinate, which can be completely wacky. So what do we do? That's what the range tree shows you how to handle, right? So you've seen this before? Anyone else knows what to do here? Okay, so here's what you do. At every vertex, you essentially will have two trees. Okay, the one tree is basically what you see here. That's this guy here. So for this node, you have a subtree, and that subtree is what you see here. But this is only the x tree, right? What we are going to do is we are going to attach to this node a different tree that has the same points, but we're going to have all its y coordinates in a nice subtree. All right? And it turns out that if you do this for every node in this tree, you get what's called as a range tree. And then I can easily search for a rectangle in here by doing some appropriate stuff. Essentially, I have to go to every node here, go to its subtree, and for each of those subtrees, I have to figure out which part. Remember, in here, I can only look at y coordinates. I cannot look at x coordinates. So now what I'm going to do is, here I only looked at ax and bx. Now here I'm only going to look at ay and by. And I am going to report everything in here that lies between ay and by. And remember, these guys are only the ones that are between ax and bx. And so I can now process this in some meaningful way. So with some extra stuff, I can answer range queries like this in 2 dimensions somewhat easily. Now, if I want 3 dimensions, what do I do?
The same process
The same process, except that every node here will have another tree that will be only z coordinates. Okay. So it turns out that in this kind of a situation, I can answer range query questions in not log n time, but log squared n time. Hey, Dimba. So here, the time complexity is going to be log to the power k of n, where k is the dimension of your space. So if k is 2, it's going to be log squared n. That's the time in which I can answer queries related to how many there are. If I want to answer queries related to which ones they are, it's a little more work. Okay? So if you have code for this, you can easily solve lots of different problems. Now, how is this triangle containment problem a range search problem? That's what we have to answer next. Okay? And I'm going to tell you very quickly, but then I'll leave it to you to figure out some of the details. Okay. So what do we have here? Come on. Yeah. So we have something like this. We have this wall, and for any given triangle, we want to know which points are in that triangle, which of the treasure points are in that triangle. That's our job, right? Fortunately, this is a static problem. It's not a dynamic problem, so in some sense, it's a little bit easier. By the way, static problems are a lot easier than dynamic problems. Even the data structures can be simplified a lot. But if you're going to your next competition, I recommend that you have range search code in your box so that you can quickly take care of this. Now let's see how we can turn this into a range search problem. So here is how this works. Here is my wall, right? So this is my wall, and my triangle is going to look something like this. It's going to be some point here, and the 2 other points are the points of the wall. And I need to know which points fall in this triangle. Once I know that, I'm just going to add them up, and I'm done. Now, how do I do this? Well, here's how it's going to be. At first, I am going to forget that I have forget that I have 2 green lines here. I'm going to only focus on the first green line. All right? Now, here are all the treasures. Those are my treasures. Okay? What I'm going to do is the following. I'm going to start from here, treat that as the origin, and I am going to draw lines to each of my treasure points. Okay. Now I can sort all of them according to polar coordinates. Fine? So essentially, I will get some sorting of the points with respect to this point. Next what? I'm going to do the same thing, this time with this guy here. Okay? So if I do it with this guy here, I'm going to get something that looks like this. Right? And again, I can sort it. I'll get a different sorted order. Now what do I do? So
Based on that point that they touch in that one. No. That one we look up. We look for no, the other one. Yeah. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. So we look for the one that they touch. Okay. based on that, we look for the 1 point contained.
Right. So now I'm going to imagine that I have queries. The query is going to be any of the points from here. It could be this one or it could be any other one. But I have to figure out for that query. So for any given query point, if this is my query point, these 2 points are of course fixed. And this triangle now gets fixed. I need to know how many points are in this triangle. Right? Now, what are the properties of the points that lie in here? That's what we have to think about.
I didn't miss the first step about the ring search, but I'm assuming like since you're using like ring search,
Yeah.
you can find all the points above one line, and you can find all the points below the other line. And
That's right. So that's what we're going to do. Okay. So remember what I did was I took this point and I sorted everything according to that. Well, I can actually give it polar coordinates based on this guy, right? So think of those polar coordinates according to this guy as my x coordinate. All right. Then I do polar coordinates according to this guy. Think of that as the y coordinate.
So for every point, we have 2 angles, one associated with the left one and one associated
That's
with
right.
the right one. And you have to find what's in between, if it lands in between the 2 angles.
That's right. And will that now fall in that triangle? Are you sure?
Well, no.
You're almost there. So that's the last part that you have to think through. So think of anything that's to the right of this guy here, right? So let's say I fixed these 2 wall points. I'm now picking one of the treasures, right? So I will get a polar coordinate for this guy. I know exactly which points are to the right of it, right? And then, well, not completely to the right of it. There may be points in here. I can cut it off with this x-axis here, right? And then I am going to, so remember, this guy has a certain x-coordinate, which is the polar coordinate of this guy, and you want everything to the right of it. So that's the same as saying if this is my, so I am looking at everything that is to the right of this guy, right? So think of this as the polar coordinate, but with this guy, with respect to this, with respect to this point. Think of this as my y, and this is my theta y. So I want everything to the right of this, and for the other one, I'm going to get again polar coordinates, and I want everything to the that are less than this polar coordinate. So if that angle is somewhere here, we want everything that's over here. Is that clear? We want the x polar coordinate to be larger than whatever is determined by that red line, and the green one to be smaller than this, right? And so you essentially get a rectangle, and it's just a rectangle query after that.
But isn't it the opposite, the left one?
It may be. What am I doing wrong? So you want all the polar coordinates smaller than this guy, so that should be less than this, no?
Shouldn't it be greater than? Because I'm thinking of like starting from here.
Oh, you want to? If you start from there, it's different. But polar coordinates go this way,
Oh, they do.
right? Yeah.
Okay, I didn't know that.
Oh, wait a minute. Maybe you're right. Sorry. No, actually, you may be right. So it all depends on what conventions you use and what's positive and what's negative. Yeah, I think you're actually right. So it may be this rectangle instead. I'm not sure. You're saying it's actually this one here, right? Could be, yeah. Either way, it's a range query problem, and that you're pretty convinced of, right?
Is the angle enough? Don't you have to also look at distance?
So yeah, so that's the thing we need to work on. What else do we need? Do we really need distance?
I don't think so.
Anything that's to the right of this? And we've cut it off over here, right? And for this guy also, we've cut it off. So it actually looks something like this. We've got the wall here. We've got this red thing. And it's going to be cut off with this, right? And then we're saying that line. And we're going everything underneath here. Seems right to me. Right? So essentially by changing thinking of polar coordinates as your x and y coordinates, we've converted a rectangle into a triangle here. That's essentially what we've done.
So we basically store like an associated angle for the x and y for every point.
Yeah, exactly. That becomes your x coordinate, and then you just plug it into a range search app, or sorry, procedure, and you're pretty much done. Okay. So you just have to convert it into a range search problem, and then pretty much you should be done. But here there's a little more work because each of the treasures has a little cost. And so you're doing a little sum. How that's handled is a minor problem. You have to kind of think about this a little bit more. But you have to actually, it's not enough just to do a regular range search. You have to do something called a weighted range search, because each point now has a value, a dollar value associated with it. Right. And so anyways, there's some more work. There's some more bookkeeping that you have to do within the data structure. But are you good with this? Can we move on to something else? Because we can't discuss range search right now. We just don't have enough. We don't have the foundations. We have to first go to 1D and then we'll go to 2D. Are you convinced you don't need distance? Yeah? Okay. All right, let's talk about the next problem. Demba, you're okay with what you saw?
Yeah.
Did you guys have range search code with you when you went?
Yeah.
You did? Okay. So you could have solved this theoretically.
Actually, I don't know, with the time we had,
Yeah.
we made it just in time. So.
But not all three of you were busy all the time, even though you were using the machine all the time.
I think we used the machine all the time, and everyone was working on something throughout the whole contest.
Yeah. Okay. So we have choice between that and alchemy. Which one do you want to look at? I don't really care.
This one?
This one? Okay, this one, fine. Somebody wants to describe this problem for me?
I didn't read this one.
You didn't read this one? Okay, anyone who's read this one? Demba, you want to tell us?
I didn't read it, but
You didn't read it? Hey,
I
you.
did read it, but I might have to read it again.
Yeah.
From what I remember, it's
Yeah.
you have like B and then you have P, and then like B is a base number and P is the power.
There are two people.
Yes.
There's a fixed total amount of money that they have.
Yes, and now they want to do a transaction,
Yeah.
right? But they want to do this. They want to fulfill the purpose of that transaction in as little amount of steps as possible.
Okay, and what is the what is the final goal of these transactions?
I don't remember exactly, but I think someone is sending.
The final goal of the transaction is that one person needs to have all the money. Okay, they don't care who has all the money, but we have to transfer all the money to one person. Now there are rules for transferring, and what are the rules?
I don't remember. I remember that on the day of.
You remember more?
Yeah, you can send.
You can
B
only
to the one
transfer multiple of power of 2 from one person to another.
Or B.
Power of 2.
No, B.
What do you mean power of b?
Because B is the base.
Oh, b to the power b. Okay, fine. Yeah, yeah. Well, yeah, I keep thinking of b as 2, but you're right. It's actually not 2. Fine. All right. Yeah.
Only constraint, like that has to be a power of b.
Yeah.
That's it?
The transactions have to be only a power of b.
But it doesn't matter who is it like in order?
It doesn't matter in who sends to whom. In the end, one person should have all the money.
So just maximize the amount you're sending.
Right. So, to me, it's very helpful to just think of B as 2. It makes it a lot easier to think about what it is that you need to do, and it'll become clear to you what needs to happen as we do this. So for today's discussion, let's fix B to be 2. Okay. All right. So then what? Again, it goes away. All right. Okay. So if B is 2, we know that initially the total amount of money that they have is 2 to the power p, right? And you can only transfer 2 to the some power from one person to another. But in the end, there's a quantity that you need to minimize or maximize. What's that?
The number of exchanges.
It's not the number of exchanges. That would be too easy, it turns out. It's actually a little bit more. So let's take a look. Sorry?
It says that the busiest player. So
This one. You want so let's say one of them transfers x times, the other transfers y times. If x is larger than y, then you want to minimize x. You want to minimize the larger of the two. Is that clear? So it's a little bit different from just saying the total number of transactions. So if one person does all the transactions, and let's say they would do it in, say, 5 transactions, that's not as good as both of them doing it 4 times each. Okay? So that's now that we understand the problem, let's try and figure out what's going on. So first of all, I said that we're going to assume b equals 2, which means that I can think of all of this as a binary number, right? So that means that so I have Alice and Bob here, right? Yeah, so this is Alice and this is Bob. I can assume that Alice has the following amount of money. And the question is, how much money does Bob have? Well, for that you have to know what the total amount of money is. And we know that the total amount of money is also a power of 2, right? And So we're going to start with that, and the total is going to be 1 followed by all zeros. So that means this is roughly that minus this, right? And what is that going to look like? You just said something. What did you say?
You flip all the bits.
Do you flip all bits? Is that correct?
Maybe not.
Sorry? Actually, yeah, let me flip this 1 to a 0, just for the heck of it. Sorry? So whatever this number is, this plus this should give you that, right? So what is it going to be over here? A 0, 0, wait. This is going to be a 0. Do you believe that? No? What doesn't add up? Where?
In the fourth digit? No, but in your right. In your left, I mean. Yeah, that one doesn't matter.
This one doesn't add up. So 1 plus 1 gives you 0, then 1 plus 1 gives you 0, then 1 plus 1 gives you 0, 1 plus 1 gives you 0. Everything seems fine.
But after that, it should not.
Sorry?
So flip all the bits after the first one.
That's right. Are you convinced? Did you understand what he said?
Yeah.
So you leave out these trailing zeros. Forget about all of them. Don't touch them. They're all going to stay as zeros. Once you get the first one, make that a 1 here also, and then everything else gets flipped. So all of this gets flipped, except for this position here, where it's the same. Okay? Now, by the way, if b is bigger than 2, then it gets a little more complicated, but you can kind of figure this out. You can see how it generalizes. It's not that complicated. All right? Now, if I were to go with the easier problem that Ian mentioned, namely, what if I want to minimize the number of transactions? What should I do?
Take the one with the smallest amounts of bits that are 1 and make like every
Send that many
transaction
ones.
is that like a power of 2 of that number to the other.
So you're saying here I have 5 ones, here I have 4 ones, so I should send all those 4 ones down here. That's what you're saying?
Yes. Yeah, that's what I think.
Okay. I don't believe that's right. Let me tell you why. So imagine that, so remember these last 4 trailing zeros I don't care anymore, right? They're not going to be part of my discussion anymore. So I have to make a decision on what to do with this one. Either Alice sends to Bob or Bob sends to Alice. Now which one would you prefer?
Bob, right?
You want Bob to send the money.
No, the one that you said is
More ones, but Bob has more ones. So you want to, that's your logic for why Bob should send the money?
H would be the one sending the money because it's the one with less money. Therefore, you have to make less transactions.
Both your answers are right, but your reasoning is wrong. Let me tell you why.
Go with the least one.
What happens when Bob sends the money over? Then 1 plus 1 becomes 0, right? The next one also becomes a 0 automatically. This one also becomes a 0. So I've cancelled out 3 ones in one shot, in one transaction. Right? So by one transaction going this way, I have cancelled out all of these. Now I have a 1 over here and a 1 over here, and I restart the process. Now who should send the money? Now Alice should send the money. Why? Because you're still going with the same reason, and which I told you is wrong. So you're saying by that same logic, you should have Alice send the money. Is that the right logic? Sorry?
Should be Bob because he has a 1, so they can.
Wait, if Alice sends the money, then it's over, right?
If Alice sends the money, then 1 and 1 will become, no, then it'll clean up until here and stop here.
I think for consecutive ones, Alice should send the money because he covers more.
So it's only one of them will cover more ones, right? And who has the ones? It's remember what will happen is that if you have 2 ones, the next bit, only one of them has a 1, not both of them, right? So let's assume this person has a 1 and this has a 0. That is enough to tell you that this guy, that lower one should send to the upper one, because that will take care of 1 extra 1, or maybe more ones if there are more ones. So it all depends on what that next bit is. So the one with the 0 sends it over. And that's all you need. So if you look at it that way, how many transactions do we need? So we need 1 here, and then it'll come down to here, and at this point you will send it this way, right? And then it'll stop here, and then I'll send it that way, and then,
No, you said that one.
oh sorry, I send it the other way, yeah. I send it this way, and then I'll be done. So 3 transactions is all I need, if all I'm counting is number of transactions. But that's not what we have to minimize here. Demba, you're going to ask something?
No, I'm just trying to see the transaction. So the first one sends up, it cancels out 1, 2, 3. Right?
Yeah, it'll cancel out all the ones. All the ones next to it will be wiped out, and this 0 will become a 1.
Become a 1, and then you send.
And then you send it down so that these 2 ones are gone. Then this becomes a 1, and then you send that again, and it wipes out all these, right? So an easier way to think about this is the following. One of them has something that looks like this. Well, actually, both of them have something that looks like this, right? The first one, both of them are going to have 1s, because all the trailing zeros are going to be common. So over here, whoever has the 0 will hold off and will send their one bit over to the other guy, and this will wipe out everything until this next one. And you'll end up taking care of all of this, and you'll end up with a 1 here, right? Then again you will send. So if you had a situation like this, then each time it'll be going from top to bottom. But it's possible that in some cases maybe you have more 1s, right? Then your situation will change, and instead of that person sending down, you're going to send this one up. Okay? So you have to decide based on what that next bit is, essentially. Yeah.
If both has like 0, 1, 0, 1, then how you will decide like?
It's not possible. Why is it not possible? That's what we said. That's why I said, look, figure out the structure first.
Oh, okay.
Right? The structure we said was trailing zeros, then 1 on both sides, and then after that everything is complement of each other. So it's never going to happen. And even when you start to wipe out these ones, all it'll do is it will wipe out all these zeros, it'll wipe out all these two zeros, and your trailing zeros will increase, and the last one will become 1. So it'll go back to its old structure, which is trailing zeros followed by 2 ones, followed by everything that's flipped. Right? So we can see exactly what happens if all we care about is number of transactions. Now they've changed the problem to minimizing the largest number of transactions by the center. Right? So that's a little bit different. So what do we do now?
Do we want to try to set up longer chains of ones?
Sorry?
Do we want to try setting up longer chains of ones?
You can't change the configuration.
Okay.
You're saying transfer it so that you get a longer chain? Is that what you're saying?
I don't know if that's possible.
Look, the problem is that under this consideration, which we use right now, namely minimizing the number of transactions, it's always the ones with fewer ones that are sending it over. We want to reverse that. We want to say, okay, what if I could reduce the number of transactions by having this guy send a few over? Remember, this guy has 0 transfers. We have if the number of transfers you're doing is k, then I can increase this all the way up to k minus 1. And if that can somehow reduce the number of transfers from above, I've achieved something, right?
Mm-hmm.
So I have to do something more in order to make that happen. Yes, Timba.
I don't know, but like just based off of what I'm seeing, like we have a decision to make at every point, right?
Yeah.
And we're also trying to minimize the number.
Yeah.
So can we like use DP?
You could use DP. So there is definitely a solution using DP. I'm trying to. At least based on my understanding, for b equals 2, you can do there's a simpler solution. For b greater than 2, my guess is that you will need a DP. Yeah.
To sort of fix the minimum issue,
Yeah.
just what my intuition tells me is maybe we binary search the answer. We binary search what we say like the busy player. Like he could only do this many transactions.
But binary search, okay, so let's say I do a binary search and say, instead of this guy sending 5 times over, why don't I see if I can do with 4, right? Or why don't I see if I can do it with 3? Now, how can you decide that you cannot do it with 3
I'm
transfers?
saying, like, let's say we assume the busy player does k transactions, at
Yeah.
most k transactions. And if I know that's possible, then I know everything from k to k minus to 0 is possible. So now
Yeah.
I search from everything to the right of k.
Uh-huh.
So that's why it's monotonic.
I see. Yeah, yours is a different solution. I'd have to get my head into it in order to think. So let me give you what I think is my approach, and then maybe we could explore yours a little bit more. Before I carry on, any other thoughts? So, yeah.
Can you show an example where this approach doesn't minimize the cost, and then maybe
Yeah,
it'll help?
sure, I'll show you. So, so I'm going to redraw this. Here's a 1, 1, 1, 1, 1. So I have 7 of these, right? Let's assume that everything else is a 0. Fine?
Okay.
And over here, other than this first one, everything else here it's all flipped. And in fact, everything else is a 1, right?
Yes.
If this were the situation, let's assume this thing is packed with 1s, okay?
Yes.
In this case, clearly, in 7 transactions, I'll be done,
In 7 transactions will be done.
right? Because I'll send this one over, it'll flip everything until here, then I'll send that bit over. So just sending all the 1s over is going to take care of it. Fine? Okay. So now I have to somehow get this down to 6, if I can. Now how do I do this? Well, here's a possibility. Let's assume that between this 0 and this 0, there's only 2 1s. Okay? Now what will happen? So I'll keep the old solution until here. Until here. Yeah. And then when this becomes flipped to a 1, I am going to send this over. What will happen? That 0 will become a 1. And then I'll send this over, and I'll send this over. Okay, so now I've sent 3 from the lower side. And what will happen is this one goes up, so what's going to happen? This one goes up. Yeah, that would have been flipped to a 1. It'll become a 0, and this will become a 0, right?
Wait, because you sent.
This had become a 1.
Yes, that one became a 1.
I send it up,
You send it up and then it changes.
and then that changes this one to a 0, but this 0 will become a 1,
Yes, and then okay,
right?
that
And then again, I'll send this over. That'll become a 0, and this 0 would become a 1. Then again, I'll send it over, and then this would become a 0, and I've taken care of all of this. So now what I've done is I've reduced the number of transfers from above to actually 2 less, it seems, right? Because even this one I didn't need to send, that became an automatic 0. So now I have zeros all the way up to here. Correct?
Do you have zeros all the way up to there, or do you have a 0
Oh,
and a 1?
maybe until here, right? Okay, fine. Yeah, you're right. So I still have something over here. So at this point, yeah, right. So until here. So at this point, I could still send this one down,
Yes.
and what I've done now, what I've achieved is I've reduced the transfers from above to 6, and the below and the transfers from below to be 3, which is a better solution than 7 from above and 0 from below. You believe this?
Yes.
So similar things could happen where I could start to transfer more things from below and reduce the number from above. So the only way this can happen, are you guys understanding this? So the only reason it happened was because there were not many 1s between these zeros, right? And because this number was small, I could send each one of them above, and it ended up saving me. So essentially, these are blocks of 1s. If you send it from above, it will wipe out all those. Otherwise, all those 1s have to be sent one by one above. So that means our cost depends on how big each of these pieces are. Is that clear? So think of these as, say, A1, A2, A3, A4, A5, A6. Something like that. Will that So now what should my decision be based on? That's the question, right? Yeah.
Maybe we have like, we know the sizes of the A's, right? The smaller A's, right? And I think it will be more optimal to let's say we've already solved it the naive way. We have
Yeah.
the total number of transactions that
Correct.
we need
Correct.
to solve the whole problem.
Yeah.
And now we're trying to minimize this number.
Correct.
So the way we minimize this number is if one A could flip things less than the number of transactions.
That's
then
right.
We go for that A and then B.
Yeah, so essentially that becomes a greedy algorithm,
Yes.
right? You're saying which of these A's is the smallest? I'll just wipe that out and reduce the upper one by one.
Yes, as long as the cost of wiping it out is not greater than the cost of fixing it.
Exactly, yeah. So I have this number k, which is the number of transfers I have from above, and as long as one of these is less than k, I can reduce it by at least one. Now I can keep doing that because now then that k will become k minus 1, and then I have to look at the next biggest one. So I'm guessing that a greedy algorithm would work here, and I can just go from the smallest to the largest.
Makes sense.
Now, unfortunately, I'm not sure. I haven't really thought this through. I'm not sure if it works for b greater than 2. So what is b greater than 2? So if b is 3, then you're looking at a ternary system instead of a binary system, right? But the good thing is that this complement stuff is still going to happen, except the first one is going to be what? Yeah, so the first one will be, so it's also a complement then, is it? Yeah. And then what is it here then?
Isn't the first one complement plus 1, and then everything else is complement?
Is complement, yeah. Yeah. Well, if it's ternary, if this is a 1, this would be 2, right? And over here, if this is a 1, what's this going to be? It's going to be one less. So it's going to be, here it's going to be 1 and 2, here it's going to be 1 and 1. So the sum has to be 2, not 3 there, right? Because you're going to get a 1 carryover from the next bit. So you have to account for that. Yeah, right. In fact, that's what we did. We said that each of these adds up to 1 because there's going to be a 1 that's carried over from the next lower significant bit, whereas for the last one it's just going to be a simple complement that adds up to 0, right? So anyway, knowing that, you'll be able to now figure out what is happening with the situation. The situation doesn't change a whole lot, but there you're only sending over a power of 2. What does that mean? So if there is a number 2, you can't send 2 over, right? You have to send it in multiples of b to the power p, right?
Yeah.
So if this number is 1 and this number is 2, then you can you have to take the smaller of the 2 and send it over if you want to minimize the number of transactions.
Maybe you don't always know that. I think Demba might be right with the DP.
Oh, I'm pretty convinced that you're going to need DP. I haven't worked that out at all. But I thought this would give you a framework for you to think about how DP should be approached. If you do, please let me know. I haven't quite worked out the details there. But hopefully this helps you to at least start to think about this. It looks like B can be as high as 100, which is annoyingly high. B is as high as 100, and P, what is P? That's the number of digits, yeah, up to 1,000. Whew, yeah, we'll have to see what the algorithm. Well, dynamic programming should probably be at most B times P. That's my best guess. So you're probably okay.
B squared.
B squared times P. Yeah. Yeah. Right. Are you okay with this? Can we talk about alchemy and? Does it look more doable now? Well, the DP is still quite hard, but at least you should be able to solve this for B equals 2, right? Okay, what's alchemy? Anyone wants to describe the problem for me?
You have a string,
Right.
and you want to turn it into a palindrome.
Yeah.
You can do one type of operation, which is you take two adjacent characters and you switch both of them
Right.
to a different character.
It cannot remain as the character it was before.
Yeah, that's the only restraint.
Right? And you're not allowed to turn one character at a time. You have to do two adjacent characters at any given time. Right? Those are the constraints.
Can you turn them into each other?
You can turn only if they are different from what they were before. Sure. Yeah, you can turn it to whatever you want, as long as you're changing it. Okay. And what are you trying to minimize? The number of these edit operations, right? Okay. So, any thoughts on this? What do I do? By the way, in a palindrome, if it's an odd number of letters, the middle letter can be anything you like, right? And if it's an even number, then the left side needs to be exactly equal to the right side, right? So how do you guys think about this? I'd like to know. How does this problem appear in your head? Any volunteers?
Yes, I can go. So I see it as you kind of start from the ends.
Uh-huh.
I don't want to mess with the middle. We can see
You don't want to mess with the
sort of
middle.
the stopping point, but
Okay.
I don't really know what to change. It might not be optimal to change.
Yeah.
How can I say this? In one operation, I may not want both letters at the ends to be equal. I may want to do both changes to both
Yeah.
ends. So maybe I think of a DP solution.
So you're saying you're going to take this character and its partner on the other end,
Mhm.
and you're going to mess with them,
Okay.
and you're going to do this one at a time.
Mhm.
But if you do this, then you're almost committed to n operations, which is the number of characters. Right. So if your sequence is of length 2n or something around 2n plus 1, it doesn't matter. You're committing yourself to n operations, which doesn't seem optimal to me. Right?
I mean, I'm committing myself to an operations.
Mm. All right, let me give you an example. So let's say I have A, B in this end, and over here, CD. You are committing yourself to one operation for this and one operation for this.
So I'm saying like you have sort of three choices. You can either do an operation on A, B.
Well, you right now you told me you're taking the character and its partner and messing with it.
They have to be, no matter what, at the end of the day, they have to be
Correct. Understood.
the first and the last.
Correct.
So we have three options. We can either do an operation on A, B.
Right. No, I understand. So, AB.
Yeah, A, B. So
Okay.
basically
You
it's
didn't
at
tell
the
us
end
that part of that. Okay.
Yeah, I didn't fully explain.
Yeah.
But we do an operation on A, B, so it changes to A now becomes D.
Yeah.
And then we're free to change B to whatever we want.
Right.
I can, whatever.
Yeah. I could change this to DC and I'm done.
Yeah. Or I could also do the same thing, but for CD, which is the other end. Or the third operation, I can do AB and CD. It might be optimal to change both of these.
What if we first keep track of all the letters that are the same?
Yeah. Those are. Let's assume that they are. We've kept track of it, and let's assume that we're looking at either end and they're different. And he's saying that you still have. Different choices. This is what you're trying to say. So let's assume that these two are not the same as those two. Okay. And you're saying instead of me changing all of this to DC in one step, you're saying it may actually be better for me to do an operation here and an operation here. Give me a condition where that could be true.
Let me think, maybe 4 letters? I have to write this down.
If it's 4 letters, that's a different deal because then you're talking about the middle. Let's assume it's not the middle. Let's assume we haven't quite gotten to the middle. Because somewhere in the middle, the last step has some funny stuff going on, and we can talk about that. If you're not anywhere close to this middle, I'm claiming your third operation is simply unnecessary.
What was that operation again?
So I'm saying if it looks like this, I just change AB to DC, and I'm done, and I move forward. Sorry?
The problem is that might not be possible because when you change AB cannot be equal to what AB was, and then
No.
DC cannot also be equal to what it was. Yeah, maybe it's possible.
No. I mean, B is not the same as C. Otherwise, I don't have this concern, right? And A is not the same as D. That's without that, I won't have this concern. And which means I can always change A to a D and B to a C, and there's no problem with this. And I'm saying I'll just need one operation here.
To make them equal, yes.
As long as it's not close to the middle. Close to the middle, I agree that there are some other possibilities.
Yeah, that's true.
But if it was AC and CD?
If there was, that's different. That's a different condition. I'm going to talk about that next.
In this case, yeah, I agree.
You agree? Okay. All right. So here is where I'm coming from. I'm saying the second half. Let's just forget about it. The only reason we're going to look at it is to know whether this is different or the same from what we have over here. Okay. Other than that, I couldn't care less what's there. Okay. So my suggestion is to convert this into, at least the way in my head, I think of this as a binary string, where all I need to know is this same as that, or is it different from its partner? Okay.
As in the other half, or
as in the other half, yeah. Each one has a partner if this string is ever going to be a palindrome, right?
Yes.
And it needs to be identical to its partner. So let's just say that if it's 0, I will call it identical. And if it's 1, I'll say it's not identical. All right, so I'm just going to convert this into a binary string. and I am going to get to the middle, and it's possible that I need one more thing here. So either it's going to be 1 and 1, or it's going to be 0 and 0. Fine? Now I start from this end, and I'm going to look at a few cases. What is my final goal, by the way? My final goal is to make everything identical, so therefore each of these is going to become a 0. Right? So now I do the following. If I have two 1s, then I need only one operation, because this is not the same as its partner. This is not the same as its partner. I'll change both of them together in one flip, and they will both become 0s. So two 1s become 0s in one flip. So a 1-1 condition, easy to make it to 0-0 with one flip. Are you with me? So the weird cases are 1-0 and 0-1. All right. Now, by the way, if it is 0-1, I'm going to ignore this 0. So I'm going to take this 1 with the next bit. And so therefore, I don't even have to consider this case. And I am going to just go with 1-0. Okay? Now, what does 1-0 mean? 1-0 means that this last character is different from its partner, but the next one is fine. And the problem is, in order to change this, I have to change this as well, and it's going to mess things up for me.
But you can do that in 2 operations, right?
So I can do that with 2 operations, but that's not always the best thing. And this is where I need a little more work. So that's what I wanted you to think about this a bit more. What do you think will happen? So I'm going to look at one more bit here and think of these two cases, 1-0-0 and 1-0-1. All right. If it is this, then I am going to use 2 flips in order to do this. So when I flip this one here, it'll end up messing this one up as well. So I'm going to flip this to something that's different. I will end up flipping this also to something different, and then I'll flip them back to the right ones. Does that make sense? So I'm going to do this, bring this back to 0-0-0 in 2 flips. What about this one here? Is it 2 flips, by the way? Yeah, right.
Wait, can you repeat why you converted them all to 0s? Why not just take the last 2 and just flip them to 1s? Oh, sorry. No, I had them confused. One is not identical, and 0 is identical.
Right, correct. Now I could have done flip this and then flip this, and then this 1 would have gone here, but then I would have ended up with 0-0-1, whereas now I end up with 0-0-0. Okay. If it's 1-0-1, what are the operations I'm going to make? By the way, with 1-0-0, I'm going to go to 1-1-0, and then I'm going to flip to to 0, 0, 0. Okay, that's 2 flips. Yeah.
I believe there might be some information being lost because you cannot convert, you have to convert into a different letter.
Yeah, and that's easy to find.
Like 100, we can say it's A, C, D, D, C, D.
Okay.
Once you do a flip on AC, becomes.
I can decide what letter I want to choose.
Yeah, but then
So-
the D has to change, and it won't be the same as the other one.
Well, so what are your letters now?
Could you do an example of like A, C,
Yeah.
D, D, C, D?
A, C, D, D, So-
C, D.
C, D. Like that?
Yes. So what would be the
Okay.
operation?
So here, I'm essentially taking a 1 here because that's different. That's a 0. And then here, there's a 0, 0. Right? This is what it looks like for me. So all I'm going to do is I need 2 steps to fix this, and then I'm done.
Wouldn't it be 100? I was under that impression.
It is 1, 0, 0, but as I said, I'm going to take 1 extra bit from the second half. That's for, there's a weird case at the end. We'll talk about that in a bit. If this were longer, you won't see this problem. If it's 101, what do I do?
You convert to
I can convert it to 011, and then another flip would take care of it, right?
0, 1, 1, yes, and then another flip will take care of it, or 1, 0, 0, and then another flip will.
100 is bad news because then I will need 2 flips to fix it.
0,
Yeah.
1, no, I don't want to.
So I'm better off going to 011, and then with just 1 flip of this, I can fix this to 0, 0, 0.
But also
Right.
1, 1, 0, right?
110. Yeah, that's the same. Yeah, sure. Okay. So this again is 2 flips. So with 2 flips, I can take care of this situation. And that's pretty much all the cases I'm going to consider, because I'm going to scan from left to right. If I see zeros, leading zeros, I just skip it and move forward. So it's sort of a greedy approach. Are you okay with my notation here with the zeros and ones? Because it's a little weird to think in this manner. You guys don't look too happy. Yeah? It looks okay?
Yeah.
So essentially either, as you're scanning from here to here, either you do just 1 flip for 2 of these characters, or you do 2 flips for 3 characters, and then you can keep going. Fine. And if there are any leading zeros, you just keep skipping and moving forward. Now for this middle part, if they were different, if it's 1 and 1, then I can flip both of them to a common character and take care of it. That's why it's valuable.
Could we run into a situation where we have like all zeros and then 2 1s at the end, and then it ruins everything?
No. So yeah, you can tell me what the situation is. So let's say you're saying all of these are zeros.
Yeah, but there's 2 ones as well. No, only 1 1.
Only one. So like that.
Mhm.
Clearly, if this is a 1, that's also going to be a 1, right? Because that one's also different. And you have all zeros.
Yeah.
Very simple. I take these two and convert them to a common character.
Oh, of course. Yeah.
Done.
At that point, you stop thinking. That's right.
Yeah. That's why I wanted that one extra bit. That's why this last guy is a little weird.
Can you just go over the middle part one more time? Like,
Right.
the need for the one extra?
So in the end,
Mhm.
you're either going to end up with something that looks like this,
So like you have a 1 and a 1.
a 1 and a 1, and everything else is a 0, or you might end up with a 1 here. These are your two possibilities, right?
Mhm.
So in either case, I only need one flip. If this were the case, I flip both of these. I flip this one to its partner, and I flip this one to its partner, and I'm done.
Okay, that's 2 flips.
Okay? No, it's one flip.
Wait, you flip.
It's one flip. In one flip, I fix two characters. So this guy will become that character, and this guy will become that character.
Okay, 1 flip. Yeah.
One flip. If it were this, then
And also
I just need one flip.
Okay.
So at the end, it's a little weird, for me at least. Guys, I have a meeting, I need to go. So I will pursue this later. Yeah?
Think about it some more.